Assalamualaikum and salam sejahtera to all fellow researchers. I'm Noor Fadzilah binti Ismail and I present my progress research work titled Characterization of Silver Nanoparticle Porous Silicon-Based Substrate for Detection of Low Concentration Dengue NS1 Protein. Dengue is a major international public health issue since 2015. In Malaysia, annually approximately more than 100,000 cases with roughly 200 fatal cases are reported. Early detection of an infection during the first few days is important for monitoring the patient health condition with the disease and help in reducing the fatality rate. Recently, dengue virus and non-structural 1 dengue virus NS1 protein has been accepted as an early biomarker for dengue infection. Currently, the presence of NS1 is detected through enzyme and immunosorbent assay, ELISA, and immunochromatographic ICT rapid test kit. Both tests require patient blood sample, which is invasive and prone to blood infection risk. However, the presence of NS1 protein in the saliva is far less in concentration than in blood, making it more challenging. In this study, surface enhancement Raman spectroscopy (SERS) proposed as a suitable method to detect low concentration NS1 in saliva. It is sensitive and specific technique. The performance is highly dependent on the substrate used. SERS substrate is the nanostructured noble metal which adsorb to the analyte that amplify Raman scattering. The focus of this study to fabricate optimum SERS substrate for detection of low concentration NS1. The electrochemical etching technique is employed for fabricating porous silicon, which is a variation in structural features served as SERS substrate base. The main silicon features is the high surface area. This is performed due to the etching process on the silicon surface that produces the roughness surface, which is increase the Raman intensity. The advantage of porous silicon structure is the enhancement of the Raman intensity. The porous silicon structure surface will be coated with different sizes of silver nanoparticles, e.g. NPS. Silver, Ag, is found to be capable of enhancing the Raman intensity of various molecules. Silver nanoparticles also act as shielding layer and provide long-term stability for SERS substrate layer. Then the surface characterization of the sample is investigated through the field emission scan electron microscope (FESAM) to find the optimal size of porous silicon structure performance. Finally, the substrate with an optimum size of silver nanoparticle will be functionalized with dengue NS1 antibody, and the performance will be evaluated based on enhancement factor (EF). And also the Raman characterization of the sample will be performed by evaluating the Raman signal of the substrate. It is expected that the intensity of NS1 protein Raman spectrum at low concentration will be significantly amplified to a detectable range, enabling dengue NS1 detection in saliva. Figure 1 presents the conceptual model of dengue virus NS1 protein SERS substrate. SERS substrate is the illustration of the porous silicon that being layered with silver nanoparticles. This is my current status of the research work based on the research activities and data collection that being planned through this semester. The data collection for structural, electrical, and Raman characterization to achieve first and second objectives is fully done. The data collection and data analysis for performance evaluation for detection low concentration NS1 to achieve third objective is still in progress. Dengue, okay, this is my problem statement. The dengue NS1 protein is accepted as early biomarker for detection of dengue infection. Here are the problem statement for this research. The current detection of dengue virus NS1 method use blood sample, which is invasive and prone to infection. Example of the method are ELISA and rapid test kit. Besides, the use of saliva been attempts reported in the literature, such as K.L. Anders et al. Used LISA with a reported sensitivity of 64.7%, while Mercado et al. Used rapid tests and concluded that NS1 in saliva was undetectable even in acute cases. Other than that, by using SIRS and signal processing technique, Razo et al. Reported the sensitivity is more than 80% while using commercially available SIRS substrate. The commercially available substrate used in the study is gold-coated slide. For SIRS to be accepted as early and non-invasive screening or diagnostic technique for dengue, better performance should be achieved. Thus, better SIRS substrate for detection of NS1 protein at low concentration is needed. The better performance depends on the structure physically and chemically. The SIRS substrate should form good analytic features in terms of surface enhancement factors. Okay. First objective is to fabricate silver nanoparticle coated porous silicon SIRS substrate using electrochemical technique. Second objective is to characterize the silver nanoparticle coated with porous silicon SIRS substrate in terms of electrical and Raman properties. Third objective is to evaluate the performance of silver nanoparticle coated with porous silicon SIRS substrate in detecting low concentration dengue NS1. Okay, figure 2 shows the porous silicon structure formation. It is developed in the first stage of fabrication methods. In order to enhance the Raman scattering, the DCPEC technique reported in NSM Razali's paper seems suitable to apply in this experiment because the small sample instrument production with affordable cost. Etching time duration, current density duration, and size of silver nanoparticles are the parameters taking place in the fabrication process. The effect of parameters application for porous silicon products are analyzed using structural and electrical characterization. Figure 3 illustrates the FISM characterization of porous silicon substrate for etching time of 20 minutes from top view, and the cross shape with microporous size is formed. Figure 4 illustrates the FISM characterization from the cross-section view, and the V-shape porous silicon is formed. Figure 5 depicts FISM characterization of porous silicon substrate for current density of 20 mA per cm squared from top view. So, while figure 6 depicts FISM characterization from cross-section view, and figure 7 depicts FISM characterization of porous silicon substrate coated with silver nanoparticle from top view, while the figure 8 depicts FISM characterization from the cross-section view. Okay, the electrical characterization is one of the aspects that need concentration in the porous silicon structural layer development. The effect after tuning the variable shows the electrical behaviors of the substrate development. Figure 9a shows IV curve graph of the different silicon structure with a bare silicon, porous silicon, and porous silicon coated with silver nanoparticle, while figure 9b shows the IV curve graph of the porous silicon sample at different duration of etching time. To select the best etching time of silver nanoparticles size for this work, bubble plot is used to illustrate the average current values for each setting and presented in figure 10. The size of the circle indicates the average current values obtained from measurement of current from several spots from each samples at maximum voltage at 10 volt. From the bubble plot, it is observed the variation of etching time and silver nanoparticle size does not exhibit notable pattern on the conductivity properties of substrate. This is expected since poor reproducibility is one of the disadvantages inherited by electrochemical etching methods. However, from the bubble, it is obvious that less conductivity is observed for samples with small silver nanoparticle size at 5 nanometer and also 25 nanometer. While there are 3 samples with highest conductivity labeled as T22 75 nanometer and T20 50 nanometer and T22 50 nanometer, which are selected to be tested further in the works. Raman characterization of porous silicon samples coated with silver nanoparticle was conducted. Figure 11 illustrates Raman characterization of bare silicon and porous silicon structure surface. Figure 12 illustrates Raman characterization of bare silicon and porous silicon structure surface coated with silver nanoparticle. The silvers peak at 858 and 1131 are not detected from bare silicon, but we can see while using the porous silicon the peak are visible. Enhancement factor EF is obtained from the equation of ISOs per I Raman. The concentration of rhodomine 6G used is 10 to the power of -4 molar. This will produce a good Raman intensity peak. For figure 13 illustrate Raman characterization of bare silicon and porous silicon structure surface coated with silver nanoparticle and rhodomine 6G. From the peak intensity, the EF can be evaluated by focus on the peak of rhodomine 6G such as 611 and 1510, shown as calculated. Figure 15a illustrates Raman spectra of R6G, rhodomine 6G, on bare silicon for A, B for porous silicon, while C for porous silicon coating with silver nanoparticle. What can be observed here? The bare surface structure has a smaller peak compared to porous silicon structure surface and porous silicon coated with silver nanoparticle. The R6G coating also acts to slightly increase the peak intensity. Figure 15b depict the Raman spectra of selected substrate based on the highest average current values of from IV curve. With referring to peak of SIG on 1, the T2275 nanometer give the high peak intensity, which is, we can see 23,000 something, followed by T2050 with 15,000 plus and T2050 nanometer with 11,000. The EF calculation of the substrate samples was tabulated in table 1, where samples of T2075 with EF value of 6.69. Interestingly, the enhancement factor performance is in parallel with the electrical performance demonstrated from IV curve. Thus, we suggesting IV curve performance to be used as an indicator in predicting the enhancement factor performance of the substrate. The use of IV curve in evaluating the performance of the substrate is rare and not well known. Further investigation need to be done to confirm this suggestion. For NS1 detection, the best porous silicon as the substrate coated with silver nanoparticle sample will be tested with low concentration of NS1 protein. From this research, it showed that dengue virus NS1 protein is Raman active at Raman peak of 1000 ppm, and when the concentration increased, the intensity of peak 1012 is increased. This is the current status of my research work based on the objective achievement. The data analysis to achieve first objective is successfully done with the performance comparison between the etching time duration were able to analyze. Meanwhile, for parameter of bearing current density does not give any significant difference. Only the varying etching time is decided to proceed for the next data collection. The data analysis to achieve second objective is also successfully done by electrical characterization observation and select the 3 samples that give highest current value. The Raman spectrum and enhancement factor being observed. So the sample of substrate with etching time of 22 minutes coated with 75 nanometer silver nanoparticle size produce the highest peak of Raman intensity and will increase the EF. I still work on this to achieve third objective, where the surface and functionalization process is proceeded for the best sample selected, which is T22 75 nanometer from second objective proposed, and the sample surface will be functionalized with antibody and dengue virus NS1, and the result of Raman spectrum of antibody NS1 will be determined for next observation. This list of the publication for this research work is as below. All these 3 publications are accepted and published in conference paper and journal article respectively. And there are 2 publications that are still ongoing status. Okay. This is percentage of completion of each chapter for thesis writing. Overall percentage is estimated about 50%. And what I've planned for the next targets to evaluate the performance of AG silver nanoparticle coated porous silicon substrate in detecting low concentration dengue NS1 for Raman spectrum of antibody and NS1. Successfully achieve the third objective and finish my thesis writing.